right, so today's topic, I want to look critically on those vital parameters, okay, that is required in the structural design of our flexural members. Okay, now when I talk about flexural members, I'm looking at those structural members that are horizontally positioned in our structures. Okay, basically they transmit or transfer their loads via bending. Okay, those are flexural members. Okay, so today we are going to look at some of those vital parameters, okay, that is needed to design these members. Now, also have it in mind that when we are doing our design, we design from the top to the bottom. Okay, from the top, in this case, the slab, okay, to the foundation, or the roof to the foundation, as the case may be. All right, so when you're coming from the top, if it's a slab deck roof, definitely you consider that slab, all right, as in terms of you constitute the dead loads, as well as the life load, then you design downwards. Okay, so the important parameters I want us to understand generally in design is first and foremost, we have to consider constituting the dead loads on that slab. Okay, slab, for example, is a flexural member. Okay, now first and foremost, you have to constitute the dead load in that slab. Now, how do you constitute the dead load? You look at all the features of that slab. Okay, first and foremost, you look at the self-weight of that slab, which is very important because the slab itself has its own weight it imposes on that structure. So you must determine the self-weight of that slab. Then another aspect you have to look at is the finishings. Okay, because these slabs, have finishings on them, like the plastering, okay, the plasters, the underdeck, that is the soffit, the plastering of the soffit, it also constitutes load on that slab. Then you also look at terrazzo finishings, okay, your tiles, okay, because all of these constitute load on that slab. All right, then you also look at other permanent stationed load on that slab. Okay, now the summation of all of these is what constitutes the dead load. Okay, then another aspect you have to also look at is getting the life load for that structure, because buildings have classes. We have classes of buildings. We have residential buildings, we have institutional buildings, we have industrial buildings, where the building that houses mechanical appliances and all of that, machineries. Now all of these, hospitals, schools generally, now all of these have their various life loads. All right, for example, the life load of a residential building is 1.5 kilonewton per meter square. That is the life load of a residential building. So generally, when you're considering residential buildings in your design, the life load that you're expected to adopt is 1.5 kilonewton per meter square. Now, these are the two aspects of loads that is considered in the design of our slabs. Now, once you have gotten this, the next thing you are going to do is to come up with the design load, the ultimate design load. all right, because these dead loads has to be factored, okay, because you know in structures we normally factor the load such that if at worst condition that structure can be able to, you know, stand without any form of failure, all right. That is the essence of factoring load. Okay, so the ultimate design load is what you require to compute, you know, when you have gotten the dead load and the live load. And according to BS 81100, okay, we usually adopt 1.5 GK plus 1.6 QK. That is the ultimate design load for that slab. Okay, so you take note of that. Now, once you have imputed what the summation of your dead load, you know, in place of 1.4 GK, then you impute 1.5 QK, okay, according to if it's a residential building, you use 1.5 as your QK. Now you compute for your design load. Okay, now when you calculate for your design load, usually in slab we consider per meter run. We consider per meter run. You know, in slab, before you commence the design, you have to panel your slab. You segment your slab into panels. Then you now design these individual panels. Then at the end of the day, you aggregate back all of these panels into one slab. All right, so but for the emphasis of design, you have to panel them, segment this slab into panels, okay, based on their partitions. All right, so that will now enhance a better way of designing that slab. Now, once you have calculated for your ultimate design load, the next thing you're going to do is to analyze that structure. Okay, you analyze that structure. If it is an indeterminate structure, okay, you have to adopt either Clapeyron's theory, Clapeyron's three-moment equation to analyze that indeterminate structure, or you adopt a moment distribution method to analyze it. Now, basically, the essence of that analysis is to understand the forces that is being, you know, generated, the shear forces and the bending moment that slab, okay, if it's a continuous slab. But if it's a simply supported slab, all you need to do is to, you know, state the moment for simply supported slab, okay, which is WL square over 8. Okay, now your W here is the load. That is the ultimate design load that you have computed. Now the L there is the span of that slab, okay, divided by 8. That is the moment, the moment, the bending moment for that slab. So all you need to, after you have calculated for your ultimate design load, the next thing is to calculate the maximum bending moment that will be generated on that slab. So if it's a simply supported slab, you use WL square over 8. Then you now impute the values you've gotten from your ultimate design load as W. Then your span, which is the distance between one column to the other column. That is the shorter span of that slab. So understand that when you're designing for your slab, a one-way spanning slab, you must take reference from the short span, the shorter span of that panel, that slab panel. You use the shorter span as your L. Okay, so if for example you have a panel, a slab panel of 3 meters by 6 meters, okay, when you are now calculating for the ultimate design, the maximum moment, okay, you use 3 meters, which is the shorter span, to design for that panel. All right, so once you have calculated for your moment, the maximum bending moment, okay, in the case of a simply supported slab, then the next thing you're going to do is to get your K value. Okay, you calculate for your K value. Okay, now your K value in this case is your moment, your maximum moment that you have calculated divided by FCU, okay, BD square. All right. Now, before you go to this, you must have calculated for your effective depth of that slab. That is another parameter that you need to consider in the design of your slab. You calculate for the effective depth, and your effective depth is your overall depth of that slab minus the concrete cover, okay, minus half of the diameter of that bar that is being used for that slab. Okay, that is how you are expected to calculate for the effective depth of your slab. All right, so once you have computed that, you have gotten your effective depth, then also know that your FCU, which is the characteristic strength of concrete, is a function of the exposure condition of that structure. Okay, we can use 12, we can use 20, we can use 25, we can use 30 Newton per millimeter square as the strength of the concrete, the characteristic strength of the concrete. So you adopt that strength for that grade, the grade of that concrete in your design. So when you adopt it, and like I said, is a function of the exposure condition of that structure. So assuming you are adopting grade 25, so it means that your FCU will now be 25. So your K value is your moment, your maximum moment divided by FCU, okay, times your breadth, the slab, you know, I told you when you're designing your slab is per meter run. So per meter run, you have to convert 1 meter, okay, to millimeter, which is 1000 millimeter. So it will now be your moment, your K value will be equal to your moment divided by FCU, BD, which is your breadth, which is 1000, by your effective depth, D square. Okay, so once you've substituted these values, okay, you get your K value. All right, now when you get your K value, you now proceed to getting your lever arm factor. Okay, getting your lever arm factor. Now your lever arm factor in this case, all right, is 0.5 plus square root, you know, of square root 0.25 minus 0.9 or minus K divided by 0.9. All right, so this is how you're expected to calculate for your lever arm factor. Okay, now when you complete for your lever arm factor, you expect to have a value less than 0.95. If peradventure the outcome of your lever arm factor LA is greater than 0.95, the code according to BS 8110 says that you should use 0.95 as your LA, that is your lever arm. All right, but if peradventure it is less than 0.95, you can use that exact value that is less than 0.95. So that is what the code states. All right, so once you have computed that, you now progress to calculating for your lever arm. Okay, your lever arm, which is Z. Okay, which is Z, and your Z is your LA times your effective depth D. Okay, so you substitute those values